Welcome to our third Morse lecture of this spring. And well, I assume you followed actually the other two, so you know the speaker very well and also part of the subject. And so today Nike is going to talk about the Ising perceptron model, right?
Okay, thanks very much. Yeah, thank you very much for coming to the last lecture. Today I'll talk a little bit about the random KSAT model. So this is somewhat of a continuation of last time, but most of the lecture I hope to spend on the Ising perceptron model. So in the last two lectures, we considered this particular model, random regular not all equal sat. And the main features of the model were that every constraint involves exactly k variables, and every variable belongs in exactly d constraints, and otherwise it's chosen at random. And then the solution space is given by this set of assignments. So I want to contrast this with the random KSAT model, which was introduced before and was studied more. Which is quite similar. Again, we have n variables and m clauses where m divided by n is alpha. And again, we have edges which are labeled independently. Every edge gets labeled either plus or minus with equal probability. And again, every clause involves exactly k variables. And then the only difference is that the degrees of the variables are no longer fixed in this model. So here, every variable participates in exactly d constraints, and here the degrees are at random. And the way that you can generate a sample from the model is just start off with the clauses, and every clause has k outgoing edges. And for each edge, just choose a uniformly random variable to go to, and all of the edges go to an independent slot. So one variable might by chance receive a lot of edges, and another variable might by chance receive relatively few edges. So this is the model. And then one more difference is in the definition of the solution space. So in not all equal sat, the constraint was that the variable assignment must not be either plus or minus of the assignment on the edges, whereas here the rule is that it must not equal exactly the plus assignment of the edges. So for example, in this clause, the edges are plus, minus, and plus. And this means that on the variables which are next to that clause, the only assignment which is not allowed is exactly that assignment. So you cannot have plus, minus, and plus, but the other 7 assignments here are allowed. So this is a minor difference, but it does mean that the plus and minus spins have asymmetric roles in this model, whereas they had a symmetric role in that model. So this is the random SAT model.
So you don't have the symmetry of flipping everything together?
Yeah, exactly.
That you had before? Exactly.
So for example, here, if a variable has before it's also the case that a variable might be accidentally next to all plus signs, or it might be accidentally next to all minus signs, but because of this symmetry between plus and minus in the constraint, it is still equally likely to be plus or minus. But here, because of this asymmetric constraint, if a variable is next to a lot of plus edges, but not next to a lot of minus edges, then it will be much more likely to be plus in order to satisfy this model. Okay, so then, so I want to contrast what we know about these two models. So in the random regular and not all equal sat model, this is just a short review of what I said last time, that we have this combinatorial correspondence between clusters in the solution space and these plus minus free configurations, which satisfy some local combinatorial rules. And then the heuristic is that in the satisfiable regime, this model of plus minus free is replica symmetric in the sense that the uniform measure on these configurations has correlation decay. And this happens even though the original measure on assignments has long range correlations. And based on this idea, the proof strategy is to apply moment method on the number of clusters. So the second moment is on the same order as the first moment squared, and the first moment is close to the replica symmetric value. And so we showed this result, and then this can be used to obtain the exact satisfiability threshold for this model. And then a key feature of this model that I want to emphasize is that we're working with this plus-minus-free model. So we're interested in the distribution of this plus-minus-free variable under the uniform measure on omega. And the point is that because we believe that this model has correlation decay, it should be determined by the local environment of V. So it shouldn't matter what you see far away because it's sort of independent of things that are far away. And the local environment of the tree, of the variable, it's just a regular tree. So if you look at any variable in the graph, it sees sort of the same environment around it, which is this tree, which is degree D at the first level, and then degree K at the next level, then degree D at the next level, and so on. So how does it differ in the random SAT model? So in random SAT, it's again true that we have this clusters correspond to these plus-minus-free encodings. And it's again true that this model is replica symmetric in that we expect to have correlation decay. However, the idea of applying moment method to the number of clusters no longer works for this model. So if you try it for any alpha positive, you will have that first of all, the first moment is wrong. So the first moment will not be close to the replica symmetric value, and the second moment will not be close to the first moment squared. And a related issue is that in this plus-minus-free model, if you look at a variable in the graph and you want to know its distribution under this uniform measure, it is again supposed to be determined by the local environment of the variable because of correlation decay. But the problem in this model is that the local environment is a random tree. So the degree at the first level is a Poisson random variable. Then each clause has degree D, and then the variables again have Poisson degrees at the next level. So different variables have different environments, so different variables will have different distributions. So then I want to say what type of calculations you can do in this with these random local environments. And it turns out that in the physics calculation, having this random local geometry does not really matter. So this is why in the physics predictions for these types of models, in the setting of graphs, they typically don't matter so much if it's a random regular graph or a random Erdős-Rényi graph. And again, it shouldn't really matter if it's random regular not all equal SAT or random SAT. And in each case, you would do the same type of calculation, which is you start with a graph on n variables, you remove some random clauses, you produce these cavity variables, and then you add back some random clauses to produce the graph on n+1 variables. And the particular steps that you're taking depend on the model that you have. But the only difference between these two models is that in the random regular model, the number of solution clusters, it's given by this telescoping sum. And the reason that it's equal to the replica symmetric value is that each step of this cavity procedure is approximately the same. So each step is quite similar, and each step, the change that you have, it's concentrated around a single value, and it will be concentrated around this value. The difference in the random SAT model is that you again have this telescoping sum, but the individual steps, which I called L sub I, so the individual change that you get from adding adding a new variable, they will be different for different I, because sometimes you might happen to add a variable of very high degree, and sometimes you might happen to add a new variable that has low degree. just by the randomness of the model. So the Li will fluctuate across the different I, but the point is that you're taking an average over many Li, and you expect the average to concentrate around, again, the replica symmetric value. So this is the only way in which the physics calculation will differ between these two models, but it's quite similar. However, in the setting of random CSVs, the cavity method has not been made rigorous. So the existing proofs that we have, they typically circumvent this by using the moment method. And then in the moment method, in random KSAT, you have this obvious problem, which is that you don't have the expectation of the log because we don't know how to calculate that. And we just have the expectation of this random variable. So it's the expectation of an exponential of these sum of Li, which fluctuate. And the expected value of the exponential of a random variable is larger than the exponential of the expected value of that random variable. So this will be large. And as a result, the moment method will give the wrong answer. So this is why for not all equal set, you would expect the moment method on the number of clusters to work, and why you won't expect it to work in the setting of random KSAT. So another way of saying kind of the same thing is that the reason that this expected value is wrong in the KSAT model is that it's dominated by this rare event where you have an atypical profile of local environments. So for example, maybe too many variables have a local neighborhood that look something like this. So this is just meant to illustrate this variable has kind of low degree. These variables also have low degree. This can certainly happen by random chance, but if it has low degree, it means it's kind of under constrained. And all of the edges have the same sign plus, so it's probably pretty likely that you can just satisfy it by setting the variable to plus. And then these happen to be leaves, which means that they're, again, not constrained. So this is the type of structure that can arise by random, and it will arise by random in the graph. But if it arises too many times, then this random variable will be too large. And the reason that this expected value is too large is that it's dominated by the rare event where this type of neighborhood arises too often. Okay, so in random KSAT, one thing that you can do is try to condition out this source of extra randomness. So the idea is to do the following. Let this D sub R be the empirical distribution of local neighborhoods in the graph. So dr of t is just the fraction of variables in the graph, such that when you look at their R neighborhood rooted at the variable, it's isomorphic to t. So again, we take R to be some fixed radius, which will be very large. So because we take it to be a fixed radius, t should look like a tree. So dr is random. So when you sample the random graph, it will have some random distribution of local neighborhoods. But with high probability, it will concentrate on a particular distribution, which is which I'll call dr star. And it's the distribution that you expect to see in the random graph, which is, again, Poisson degrees for the variables and then degree k for the clauses. And all of these are independent Poisson random variables. So the intuition is that if you were to condition on the degree profile of the graph being close to the degree profile that it should be, then you would be able to apply the moment method and it will give the correct value. So the expected number of solution clusters conditional on this correct degree profile, it should be close to the replica symmetric value for this model, plus some error, which will vanish as you let R go to infinity. And the second moment should be close to the first moment squared, and again with some error that will vanish with R. So this is the main idea behind this result. The details are somewhat more complicated. So I will mention just briefly some of the ingredients that are involved. So the fact that there is a sharp threshold sequence, this is a result from Boolean analysis from Friedgut. The sharp upper bound, actually, we don't use the moment method for that. It turns out it can be proved by an interpolation bound. So this type of bound has been obtained in various works. So it started out with these two works, and then the bound that we use came from this paper of Penchenko and Talleyrand. And the main work of the paper was to prove the matching lower bound. And it turns out that the random k-sat graph is a little bit pathological. So you have to remove some things to make this kind of analysis work. So roughly the proof strategy was to take the random k-sat graph, prune away some of the most pathological things, and end up with a graph GNR, such that the number of solution clusters on this prune graph gives a lower bound for the number of clusters in the original graph. And then there's a further truncation that has to be done to make the second moment method work, because it's a combinatorial model. So if you want to prove that it's satisfiable, it's actually not enough to prove the second moment estimate up to some, so this amount of error is too much for the second moment estimate. You actually need it up to constants. So there's some further work needed for that. But the main idea is to condition on this R neighborhood profile. Okay, so now for the rest of the talk, I want to move to the perceptron model and then compare this with the random k-sat model. So the model is defined as follows. There are two versions, the Ising perceptron and the spherical perceptron. I will mostly talk about the Ising perceptron, which is that you take the discrete cube, again, plus minus to the n, and subtract this union of HA, where HA are random half spaces. And the spherical perceptron is the same, except that instead of starting out with a discrete cube, you start out with the sphere. So another way of writing this is that you let G be the n by n matrix with independent, identically distributed standard normal entries. And then the perceptron is the set of x in the cube, such that G times x, scaled by square root n, is greater than or equal to kappa coordinate-wise, where kappa is just a fixed parameter of the model. So the rows of kappa correspond to the normal vectors of these random half spaces, and the scaling is such that each entry of this vector, it will be a normal random variable with variance 1. So it's correct to take kappa to be a constant scale. And then finally, the capacity of this model, it's the largest alpha, such that the resulting set will be non-empty, either with high probability or with non-negligible probability. It's believed to have a sharp threshold in this model as well. So this is the model.
What does this model?
Sorry.
What does this model? What's its motivation?
Yeah. So there is some motivation, which I'll describe. So this is sort of where it comes from historically. So the reason people started studying this model is that they had this sort of toy problem about a neural network. You can decide if you like this problem better than the other problem, but so this problem is that you have this neural network. This are the inputs. So you feed information into each one of the nodes here, and then the network is supposed to do something, and then it will output a vector here. So it takes in a vector of length n+1, according to this model, and outputs a vector also of length n+1. And the rule of the network is the following. So for each input G, you're supposed to output an H, where the jth coordinate of H is that you, so the jth coordinate here, you take all of the inputs here, and then you multiply them by the weights of the network. So you take this sum, and then you just take the sign. So it's a simple operation. And then the storage problem is, can you choose weights on the network? So can you choose the J such that for all of the vectors that are given to you, I output a vector with the same sign pattern as the vector that was input. So this is the so-called storage problem. And it corresponds to the same model that I just described above. So the correspondence is that you take xi to be the weights of the network. So xi are, say, all of the weights going into one node. And then the entries of G are given by this transformation of the inputs. So roughly the inputs correspond to the matrix G. And then the capacity in this model, it corresponds to the, if I give you patterns at random, what is the maximum number of patterns that you can store in this network?
And how does that relate to Ising model?
No, it's called the Ising perceptron model, just to distinguish it from the spherical perceptron model. So Ising in the sense that you take plus minus spins. Okay, so I'll describe the statistical physics picture for the perceptron. So there are some differences with the satisfiability problems that I have been talking about. So first of all, obviously it's you can draw it in a similar way, which is that there are m constraints and there are n variables, and there are some interactions among them. But here, this is a complete bipartite graph. So every constraint involves all of the variables, and every variable participates in all of the constraints. But as a result, each variable participates in the constraints in a very weak way. So each variable has a small influence on whether the constraint is satisfied, and each constraint should have a small influence on the distribution of each variable. So this is different from the satisfiability models, which are they are more interesting in this regime where the graph has bounded average degree. So the prediction for these models is the following. So it was studied by physicists in the late 80s, and they predicted that for the spherical case, if kappa is positive, and for the Ising perceptron for any kappa, they're replica symmetric. So I have to say what replica symmetric means in this context. So here it's on a dense graph, so I can't talk about correlation decay in the sense that when two variables are far apart, they're close to independent, because nobody is far apart from anybody in this graph. All the variables are neighbors to each other. So here, replica symmetric, it just means if I consider any fixed subset of variables of bounded size. So if I take 100 of the variables and I let n go to infinity, then those 100 variables behave roughly independently under the uniform measure on the solutions. So this is the notion of replica symmetric in the dense setting. So then you can again do a sort of cavity type calculation, although the cavity here is it's actually even more simple, because you again have a sort of telescoping set of operations, and to get from one system to a larger system, it's very easy. You just add new rows and you add new columns, and you preserve the row to column ratio. So when you do these operations, the main analogy with random k-sat that I want to make is that the change that you have in the system when you add a row and add new columns, this change will be random. It will depend on the entries in the rows and columns that you add. and it doesn't concentrate around a fixed value. So if you take a particular one of these values, it will be random, but then when you average over a bunch of these steps, it should concentrate around some constant. And this is the replica symmetric free energy for this model. And then the critical capacity, it's the solution to, it's the zero of this function. So for example, for the kappa equals 0 Ising perceptron, it was predicted that the threshold is around 0.8 by Kraut and Mézard. And then some similar predictions were made by Gardner and Derrida for the spherical perceptron, and again for kappa, which is non-negative. By contrast, and this I won't talk about so much, in more recent works of these people, they considered the spherical perceptron when kappa is non-negative, and this is expected to be a much more difficult model. So it's expected to have full replica symmetry breaking, which is a much more complicated behavior, and not very much has been proved about it, but there is some recent work in the literature which is rigorous. So I mentioned that as an example. But I will mainly focus on this replica symmetric setting.
Excuse me, so which one has the full replica symmetry breaking?
The spherical perceptron when kappa is negative.
Well, that should be a simpler model, right? I mean, spherical model. But I guess when it's positive, it's somewhere. But when it's,
yeah, when kappa is positive, it's a convex model, and that has been solved. But when kappa is negative, it's no longer convex, and it's believed to be quite complicated, and it I think the asymptotics are not known.
But you have some reference there to Selke and so forth. So what does that do?
Yeah, I think Ahmed might be here. So I believe it's an algorithmic work. So it's under the assumption that it has the Parisi full replica symmetry breaking. They show that there is an algorithm which can sort of find a pure state of this model. If Ahmed is here, maybe
will it have one pure state, or will it have many? Or
it should have many, have the hierarchy
full,
of
the whole hierarchy
of
states. Yeah. Okay, so
that result is under a condition of full replica symmetry breaking of the Parisi formula that was conjectured or obtained by the physics people, by Mezzappa, Urbani, and at some point.
Yeah, so it's assuming that picture, it gives an algorithmic result. But the full replica symmetry breaking result is not known. If that's correct, yeah. Okay, so then I'll go back to the replica symmetric setting. So this is what is known for the spherical perceptron, and this is for the positive case. So for kappa equals exactly to 0, it was known a long time before that the critical alpha is 2, and this is by some combinatorial recursion. For all kappa non-negative, it was proved that the volume of the spherical perceptron converges to the replica symmetric formula by Sherbina and Tirozzi. And then again, for all kappa non-negative, the critical capacity, it was proved that it is given by the zero of this function by Stoinich. And all of these proofs, they use very crucially that this is equivalent to a convex problem. So in particular, this uses some like Gaussian comparison inequalities and a minimax duality for this problem. And then this is also using kind of concentration properties of log concave measures. So for the Ising perceptron, because you no longer have this convex structure, much less is known. So most of the results, they concern the case where kappa is equal to 0. And also pretty much everything I will talk about today will be about the kappa equals to 0 case. So I think for any of the results that have been proved, the kappa equals 0 is not actually important. It should be the same behavior for any kappa. It's just that kappa equals 0 is sort of a well-known case that is easy to study, but I think all of the results of any of the people that I will talk about today, some version of that result holds for general kappa. So first, for kappa equals 0, for the Ising perceptron, it was proved in the late 90s that the critical alpha is strictly away from 0 and 1. So I will show in a moment that 1 is kind of a trivial upper bound in this case, but they showed that it's strictly away from that. And then I do want to mention that this paper has also an interesting algorithmic result, which is not only do they show that, so they show for small alpha that, for very small alpha that you have a non-empty set, but they actually show an algorithmic way to find that set. So you want to find an element x, which is in the discrete cube, such that when you multiply it by g, its entry-wise positive. And the way that they do this is your matrix G. So it's when alpha is small, so it's a very wide matrix, and you want to find a G, which you want to find an X, which is positively correlated with every single row of G. And the natural, I think that the natural thing that you would first thing to do is to take the G and, for example, just take the sum of every column and take the sign of that. So sum up this column and it's plus, and then sum up this column and it's negative, and so on. And that would work pretty well because, again, it's a very wide matrix. So that should work pretty well, but it will not quite work with every single one. So on average, you will make like a small fraction of mistakes. So the idea of this paper is just to do it in a multi-scale way. So you first do this majority procedure with the first, maybe 2/3 of the matrix, and then most of the constraints will be satisfied, and then some of the constraints will be violated by chance, and then you fix these up at the next stage, and and again you will have a few that are not satisfied, and you fix those at the next stage. And this will succeed with good probability. And this is somewhat related to this problem in computer science about discrepancy minimization. So I mentioned that as a reference, but this is kind of these are usually in the worst case setting, where this is in a randomized setting. Okay, so then another result that I want to mention, which is so I actually couldn't find the date for this because I couldn't find it published anywhere outside of Talleyrand's book, but so I guess it's from his book. So this is to consider a sort of generalized model where I still sum over the discrete cube, and I take this model, which is exponential sum over A, and some function u, which is specified by the model, and u of the g times x, the 8th entry, divided by square root n. So Talleyrand considered this general model, and he shows that this also converges to the replica symmetric value in a few settings. So either u has to be nice enough, where nice enough means that u and maybe a couple of its derivatives, so maybe u and u prime and u double prime, all have to be bounded by something which is small enough. So that's one setting where this result holds. He also shows it for the model that I described, where that would mean that u is either 0 if z is greater than or equal to kappa, or -infinity if z is smaller than kappa. So for this function, which is certainly not nice in the way that I just described, he does show that this formula holds provided alpha is small enough. So this is actually stronger than the result I just described.
Does this algorithm have a standard name now, or not?
Yeah, actually, I don't know if this algorithm has it's not that I know of. It's kind of because it's kind of a simple multi-scale idea. So
Mhm.
I expect some like it probably shows up very commonly. I don't know if there is a name given to it. So the proofs of the replica symmetric formula. So so the fact that this volume converges to the replica symmetric formula. So these are in the spherical setting, and then this is in the Ising perceptron for nice U or for small alpha. These proofs are they're quite difficult, and they're based on a smooth version of the cavity method. So this symbol, this thing I took from Talleyrand's book, but it's not really meant to be parsed in great detail right now. The point is that he considers you can consider a Hamiltonian where inside of the U you smoothly remove the last spin and you replace it by an independent random variable. And maybe outside you have a random field to compensate for that. So this is like, it's a version of the cavity method where ST goes between 0 and 1. 0 is the original system, or actually in the way I wrote it, 1 is the original system. And 0 is a system where the ith spin has been, where the nth spin actually has been decoupled from the previous system. So in some cases, it's possible to prove under this Hamiltonian that you have enough concentration such that you can control how the partition function behaves as you interpolate along this path. But obviously this is easier if the function u is nice. So it's easier if you have some concavity assumption on u in the spherical case. And then in the Ising case, it's easier if you have some regularity on this u. And it seems to require a substantial work to transfer it to this original model that I described. And in the case of the Ising perceptron, it has been done when alpha is small, but it remains unclear if it can be done in a general setting. So this is the result that I will describe in the rest of the talk, which is this is a joint work with Jianding, and we were interested in seeing if it's possible to apply a moment method for the Ising perceptron model, just because it's very difficult to do these kind of smooth cavity method, and we wanted to know if you can do something more simple like the moment method and maybe get some either a stronger result or just a different result from that. So we have the following result in this setting, which is that for the Ising perceptron, and again at kappa equals to 0, this is a conditional result. So I will describe the condition in a moment. Under this conditional result, the replica symmetric value that was predicted is a lower bound for the critical value of the perceptron. So the condition, which we don't know how to remove, is that we have some explicit function s of lambda. So this is the function. It looks like that. It's too complicated to write down on these slides. So it's in the paper, and the requirement is that this function has to be negative except at lambda equals to 0 and at lambda equals to 1. So we can plot it on the computer, although from the sparsity of the dots, you can maybe see that it's not very easy to plot this function. And the method applies for general kappa and general u, but then we would end up with a different function which depends on kappa and u, so we didn't want to make any claims in general. So this is the result that I want to describe, and I will describe some proof ideas for this. Okay, so what happens when we try to apply a moment method for this model? let Z be the number of elements in the perceptron. So the first moment is extremely easy to calculate. There are 2 to the n elements in the cube. And if you put down a random half space, then it will survive the half space with probability 1/2. So this is exactly what the first moment is. And it says that in the case kappa equals to 0, the value alpha star equals to 1 is a trivial upper bound. And so kappa equals to 0 means that you have this trivial upper bound of 1, but if you took a different value of alpha, you would again have some different value would be the trivial upper bound. So however, the first moment is always incorrect. So the typical value is much smaller than the first moment with high probability for all positive alpha. And it's for extremely similar reasons as in the random SAT model. So if you want to think about it in terms of the cavity heuristic, you can build up your n alpha by n matrix by a sequence of steps where you augment the matrix a little bit at each step. So you have this sequence of steps, and in the cavity heuristic, these steps are random, but when you average over them, they will concentrate on the correct value. But when you take the first moment, again, you're taking expectation of exponential of this sum of values. So because the exponential is inside the expectation, it will give the wrong answer. And similarly as before, another way of saying it is that the first moment is dominated by the rare event of having some atypical matrix, which is favorable for having a very large number of solutions. So you can imagine, for example, that if you take the rows of the matrix and they just all happen to be slightly correlated with the all ones vector, or if on average you have if the average correlation with the all ones vector is 1%, it should be 0. But if it's 1%, this will favor a large perceptron set because all of the half spaces are kind of pointing in a closer to the same direction. So in random SAT, as I said, we resolve this issue by conditioning on this empirical distribution of neighborhoods. And the rationale for this was that we had a replica symmetric model by moving to this model of solution clusters. And then in the replica symmetric model, the idea was that the behavior of a variable depends only on what it sees in the local environment. And so if we just condition on the randomness in the local environment, then we shouldn't have this issue of extra fluctuations. And then the question that we started out with was what is the analogous object in the perceptron model? So here it's a dense graph. As I said, everyone is a neighbor to everyone else. So and we hadn't really worked with this type of dense model before, so so it was not clear to us at the beginning what is the analog of the local environment of a variable in this type of model. So it turns out that the answer is given by something called the TAP equations, which I will try to describe briefly now. So the idea is that again, let's consider mu to be the uniform measure on the perceptron set, and let delta be this 1 over square root n g times x. So the constraint is that delta is supposed to be non-negative. That's a constraint of the model. And then the replica symmetric heuristic is that these random variables are supposed to have correlation decay. So each xi individually, it's a plus minus random variable. So it's a Rademacher random variable. And so that means it's characterized by the mean, which is m sub I. And then each delta A, it has some distribution that at the moment we don't know it. So let's just call it d sub A. And again, we believe it has correlation decay in the sense that if I take any 100 of these, they will behave independently to one another. Or if I take, on the other side, any 100 variables and let n go to infinity, then they will behave roughly independently of one another. Okay, so then these things are related to these things, obviously. So for example, if you don't have this constraint that delta A is positive, then delta A is defined as 1 over square root n sum over I GAI xi. So it's we're conditioning on the instance. So it's this sum, and the xi are random plus minus random variables with mean mi. So the mean of this thing is just the mean of this is mi. So this is the mean, and we'll call it h sub a. So in vector notation, h is given by g times n scaled by square root n. And the variance of this thing, it's 1 over n. And then we're treating things as roughly independent. So it's kind of an independent sum. So 1 over n sum over I GAI squared. And then the variance of this thing, which is 1 minus mi squared. So this thing will be random, and it will be some value ha, which will be different for different a. But this value will be roughly the same for all of the a, and this is 1 minus q, where q is the scaled squared norm of m. So this is without the constraint on a, but once we put back the constraint, so without the constraint, it's a sum of independent things, so it should be roughly a normal random variable with mean h sub a and variance 1 minus q. And then once the constraint gets put back in, it's just the normal distribution, but conditioned to be positive. So this is what the dA is. So I went through this derivation just to say that it's some simple distribution which is determined by these parameters. Okay, so the dA are determined by some parameters. So I'm calling these NA, where NA is some function of HA. So it's just some one-to-one function, which is a convenient way to parameterize it. And then the conjecture is that the parameters M and N of these distributions, they are related to one another. So we saw here that the parameters of the clause distribution are related to the parameters of the variable distribution. And then it should be the same the other way. So the parameters of the variable distributions, it should be determined from the parameters of the clause distribution, with this assumption that things are approximately independent. So these are the equations. They're called the TAP equations because they were derived for a different model by these people. And in the context of the perceptron model, these are the exact equations. So just a minor comment that one of these equations is kind of in contradiction to one of the equations that I wrote up there. And this is because up here, I cheated a little bit because I said without the constraint A, I have this, and then I put back the constraint and I just made this change. So this is not exactly correct because when I remove a constraint, I also change the parameters a little bit. So I didn't account for that in this calculation here. And these equations correctly account for the change between when you remove a constraint and when you put the constraint back in. So there are some equations that relate these parameters. And then once you know this, then a natural idea would be to try to condition on these parameters because they're kind of analogous to the R neighborhood distribution in that they determine the distribution of the elements in the graph. And unfortunately, a problem here is that we don't know much about the solution of the TAP equations for this particular problem. So so of course, we don't know if the actual measure that we're interested in is replica symmetric. So if we knew that, of course, that would be great. But we don't know that. And we don't really know if it has such parameters. So we don't really know what is the distribution of the deltas. You can certainly define M to just be the mean of the distribution, but we don't know if it satisfies this nice set of equations. So it's believed to be true that if you give me a typical n by n matrix G, which is sampled from the Gaussian distribution, it should have a unique tap solution, and that should be the one that characterizes this measure. But this has not been proved to be true, and it's probably somewhat difficult to prove that this is true. So it's not known whether it's a unique solution, and it's not known whether that solution actually relates to this measure. So what we actually did in the proof is kind of a workaround of this issue, which is to condition on an iterative version of the tap equation. So we don't know how to solve the tap equations, but we can write down this iterative form of them, which is the same equations as before, but with the time index. So here it's s+1, and then s and s-1. And you just started from some fixed initial vectors. So m0 is the all ones vector with some scaling, and n0 is also the all ones vector, again, with some suitable scaling. So here, you don't need to solve any equations because you're just starting from some fixed initial vectors and then running the equations forward from there. And actually, this system has been analyzed in great detail and also in greater generality than this version that I wrote down here. But it's known in particular that it converges in this kind of weak sense that if you let t go for a long time and you look at mt and nt+1, they will be kind of close in Euclidean norm. So it's under some condition, but that condition does hold in this model. So then this is kind of a more rigorous version of what we believe to be true, but don't know how to show. And then based on that, a natural idea that you can try to do for a conditional moment method is to take the expected number of solutions, but conditioned on the realization of this tap iteration, of this AMP iteration. So condition on what is revealed in the first t steps of this and ask for that to be a typical realization, and condition on that. And it should be the case that the result is close to the replica symmetric value with some error that will vanish with t, and also that the second moment conditionally should be close to the first moment squared. So this is the idea, which we believe to be true, but actually we don't know how to show exactly this statement is true. There's some ongoing work with Irvin Bolthausen and Changji Xu and Shuta Nakajima, where we're trying to show some version of this. But the result of this paper is that we constructed a ZT, which is a lower bound on the Z that we're interested in, such that we can show a moment result, which is that the first moment is close to the correct value, and the second moment and first moment are comparable to one another. And a very similar strategy was done by Irvin around the same time, where he considered the high temperature SK model with an external field, and his result is that you can recover the free energy of this model using this method. So I'm pretty close to done. So I just want to mention a couple references, because there have been various works since we considered this problem. So there are some in the physics literature, some computational works about trying to find trying to efficiently find a solution of the perceptron beyond the regime of the Kim and Roche paper. And then more recently, there were studies of symmetric models where u of x is equal to u of minus x. So in the same way that the model I described is analogous to the random SAT model, a model where this occurs, it's analogous to the regular not all equal SAT model. So there have been papers about the threshold in this model and about the structure of the solution space of this model. And then finally, there is also a question I didn't address at all, which is whether the model has a sharp threshold. So, and this is like a Boolean analysis type of question. And this was proved for the model where the G matrix has a ±1 randomness by Changji Xu. So I think I will stop here. Thanks very much for coming to the lectures. I really appreciate it.
Thank you very much. Thanks to you for the beautiful 3 lectures. And questions?
Hi, Nike. I have a question. So if you go back to your moment computation, the error term that is exponential of n times log of t of 1, like naively, that doesn't seem to be enough to prove satisfiability, right? Because the ratio of the second moment squared over the first moment is still vanishing with n, unless you can get quantitative bounds about the little o of t of 1, right?
You mean here?
Yeah, or the equation that is right above it.
Yeah, that's right. So if you have only this with this error, it's indeed not enough. So that's why we have to construct this kind of slightly different random variable where we can show up to constants. So this is up to constants, not up to this little OT. I think this is why we have this extra step in the paper of reserving some of the last columns. That's the reason for that.
Yeah, got it. Thank you very much.
Yeah.
Other questions?
Just something that's maybe very unrelated, but when in the previous model, when you use this random neighbor, the average neighborhood of a vertex, do you use the Benjamin-Schramm estimates, Benjamin-Schramm convergence in some sense to some limiting object?
Yeah. I mean, it implicitly uses that the Benjamin-Schramm limit is this Poisson-Dalton-Watson tree. Yeah.
And then so eventually you have your object, your distribution on the random tree.
Yeah, exactly.
And then how close are you in your Benjamin-Schramm metric gives you that is this what gives you the estimate?
Yeah, I mean the issue is that like if you go to any R neighborhood, the best like distribution of R neighborhoods for the KSAT model to have like many KSAT solutions, it will not be the same as the Benjamin-Schramm limit.
Really?
Oh yeah, just because I mean if you had like all plus, that would be the best, right? Or if you had like too many plus, it would be favorable to having like more solutions. So it would be like slightly atypical for the random graph, but it's better to have more solutions.
I see.
So that's why you force it to be the typical distribution, because that's what you should see with high probability, and then the moment method should work when you force it to be the typical distribution. That's the hope.
Thank you.
Any more questions? Well, if that is not the case. So join me in thanking Nike again for the beautiful 3 lectures.